All right, so just to carry on, so this is where we're up to. We've got a dispersion relation for our waves. And we're trying to solve this for the wave speed, which is, we're trying to solve for basically omega squared on k squared to find out what the wave speed is. And we want to know what this is. It's meant to be a question mark. And so we've got this expression for our dispersion relation so far. This is the amplitude of the velocity perturbation. This is our omega, and our k's are sort of buried in here somewhere. So we got two kinds of waves, if you remember. So we got transverse modes, where v dot k is not equal to 0. V dot k is equal to 0. So they're entirely transverse to the line. So the wave vector is basically exactly perpendicular to the velocity perturbation. And the longitudinal modes, which is like a compressive wave where v dot k is not equal to 0. So the transverse is actually the easiest case. So for the transverse modes, and this is the new kind of wave that we have in MHD that we didn't have in hydrodynamics. So we have basically that term 0, that term 0, that term 0. We've only got this term left. So then we simply get that basically omega squared v equals that 0, that 0, that 0. We've only got this term left. It gives us a b naught dot k all squared on mu naught rho v. Okay, so now we can cancel the v from both sides. Now recall that the alphane speed squared we defined as the square root of b naught squared on mu naught rho is the alphane speed. Alphane as in E as in cafe. So therefore cafes which you're not allowed to go to right now. So v alphane squared cos squared theta k squared. So if we define, so our dispersion relation for our transverse waves is simply that, well, theta is the angle between magnetic field and the wave vector. In other words, b naught dot k is, mod b naught mod k cos theta. So kind of by definition of theta. Okay, so these are known as alphane waves. Alphane waves. And, well, they propagate perpendicular to the magnetic field lines. And they propagate perpendicular to magnetic field lines. So what does this mean? Well, you can imagine a magnetic field line. Imagine I've got some magnetic field like this. Well, let's imagine it being straight to begin with. This is my background field. And I'm taking a perturbation now in my magnetic field direction. And this wave propagates transverse to the field lines. So in terms of a demonstration, I'll just grab this little bit of cable, and Lincoln will hate me for it. And imagine this is your magnetic field line. So an alphane wave is basically just a wiggling of the magnetic field. And so you notice how I'm making this string oscillate in a way that's like transverse to the direction of the wave travel. So the wave is traveling along the string. So the string is like my magnetic field line, but my wave amplitude is oscillating transverse to that. So that's a transverse wave. It's called an alphane wave, and it's a brand new kind of wave that we didn't know anything about. So if the magnetic field is 0, then obviously these waves do not exist. So for example, e.g. when theta equals so cos is, so if theta is naught, then we get omega squared equals alphane speed squared k squared. All right, so hence we got a wave which just looks like our regular sound wave. So it's simply, again, a solution to a wave equation. And in our, if you think about how our perturbation travels, this is like an I, now, so this is like a kx minus omega t. So it's like a kx plus or minus the alphane speed t. So it's, again, just a traveling wave solution, but it's just propagating at a different speed. It's a different kind of wave. So we got another kind of wave that we didn't have in MHD. But we've also got some more solutions that we need to cover as well. So, so these are the alphane waves, they're the transverse waves, but we've also got some longitudinal waves as well. So let's do the longitudinal waves. So the longitudinal waves are the ones with v dot k not 0. So then the easiest thing to do is then just simply dot this equation with k, and we should be able to clean it all up. And find what our transverse waves will do. So for the longitudinal waves, dot, let's call this equation star, dot star with k to find the following. So if we dot this with k, imagine you dot this with k, then you're basically going to get that's going to cancel, that's going to cancel, that's going to be a dot with k, so that's going to cancel, that's going to be a k squared, that's going to cancel, that's going to cancel, that's going to be a b dot k. So we're going to basically have omega squared equals sound speed squared plus alphane speed squared, k squared. It's k dot k. So k squared is just k dot with itself, plus b naught dot k all squared on mu naught rho, or rho naught. Now what's left inside? So that's a 1 minus, that's a sound speed squared k squared on omega squared. And this one gives us a minus, so that's cancelled. This gives us a minus 1, right? So the 1's cancel. And we simply get left with omega to the 4th power. So we have to multiply this thing out now. Is equal to sound speed squared plus the alphane speed squared, omega squared k squared, minus sound speed squared v alphane speed squared. And again, we can replace this b naught dot k with a cos squared theta k squared. All right, so how are we going to solve this for omega? So this is like a quadratic, but for omega squared, right? So it's a quartic, but it's just like if you think about x being equal to omega squared, this is like just a quadratic equation. So this is a quadratic for omega squared. Solution is just the usual solution to a quadratic, so therefore we have this is like our x is omega squared. So it's, minus b plus or minus the square root of b squared minus 4ac on 2a. So the b is this term, so that's going to give us a k squared on 2. Yes. Yeah, that's a minus, so that becomes a plus here. So this is a sound speed squared plus alphane speed squared, plus or minus the square root of sound speed squared plus alphane speed squared, so this is the b squared, all squared, minus 4 times a times c, so a is just 1. C is this thing, so it's sound speed squared, alphane speed squared, cos squared theta. That's it. With the k squared out the front. Okay, so for our longitudinal waves, that is our dispersion relation. So that was a long time to get to that. And so these are what are called the So there's two kinds of these. So they're fast with the plus solution, and the slow with the minus solution, magnetosonic waves. And so if B is naught, these are just your regular sound waves. So hence they're called magnetosonic waves, because they just simply reduce to sound waves when you take a magnetic field equal to 0. So these are just sound waves when B is naught. And for cos theta equals 1, so the fastest possible speed you could get, we get basically that the speed, so the omega divided by k is simply the square root of the sound speed squared plus alphane speed squared. So that is the fastest possible wave speed. So when we're constructing a numerical scheme, we're going to need this speed, but the square root of the sound speed squared plus the alphane speed squared is basically the fast magnetosonic speed for the most preferential angle of propagation. Right, so in short summary, we got three kinds of waves. Now, so instead of just sound waves, we've got alphane waves, we've got fast magnetosonic waves, and we've got slow magnetosonic waves. And these all propagate at different speeds. So you can imagine how complex the behavior of the fluid now gets. So imagine like that shock tube problem, for example. Instead of having just a sound wave propagating in each direction, you can potentially have 3 waves going in each direction plus the contact. So there's much more complex behavior of the fluid in the case where the fluid is charged. And that's where I'll leave it for the moment. We've got some important other physics to cover about what happens in MHD. But I'll see you in the next lecture.